All right, everybody, we are ready to get started here. Welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today. I'm in the pilot's booth at the top of the room up here, waving my arms. Hello, welcome everyone. And today you're here to see Tour of the Universe, which is one of my favorite shows that we do because it's a little bit different than a lot of the other shows that we have during the day. So most of the other shows we do during the day are pre-recorded movies, kind of, with a short section where a presenter like me can update you on a news item in astronomy. This show is quite a bit different, though. This is a completely live show, so I'm going to be talking to you, and I'm going to be live flying us around the universe in our planetarium software, and we're going to start out Earth, and in the next 20-ish minutes, we're going to go as far out into space as we can, and we'll come back home safely at the end. All right, so we are starting out our tour of the universe today, relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And you may notice that it's pretty dark over here at the International Space Station, and that is because this is where the ISS is right now. So right now, apparently it's on the nighttime side of Earth, and we're seeing some city lights below us there. And everything you'll see today is based on actual data and images of the places we're going to visit. So I'm using OpenSpace, which is a free open source planetarium software. If you're interested, you can actually download it at home when you go home today. If you have a computer, you can download it at home for free. And OpenSpace uses all actual data. So any of the images that you see of locations, those are actual images. Any of the locations of things like stars or galaxies and such, those are actual data points of places that we have observed and mapped out where they are. And I always like to start at the International Space Station, which let me turn on its orbit for us so we can see where it's going around the Earth, because this gives us a little bit of perspective on what we're going to see today. Because today, I'm going to take you as far out into space as you possibly could go that we know of. And we're going to, along the way, check in with what our human influence is like out there in space. In the International Space Station, this is as far as humans travel out into space right now. There are half a dozen or so astronauts on the International Space Station at any one time. And they've been up there for about 20 years now. We've had people living on the ISS. But don't worry, it's not just 6 people that have been stuck up there for 20 years. They swap out every few months or so. And the longest that any particular person has lived up there was about a year. But today we'll see how far human beings have traveled in general, how far any of our spacecrafts have traveled, and how far any of our communications have traveled as well. But right now, at least, just a few hundred miles above the Earth's surface. That's how far humans are traveling into space at the moment. But there are plans in the works to send people to the moon again and to Mars as well at some point in the future. But I'm going to start zooming us out a bit here because we have a long way to go. So we're going to keep on moving at a pretty quick pace here to make sure we get to everything. And I'm going to bring us over to our closest neighbor in space. We're going to fly over to the moon. Now, when I focus on the moon, it might switch kind of quickly. So if this makes you dizzy, close your eyes for a second. There we go. And we're going to fly over to the moon. So the moon is a good next step to check in on our human influence out here in space, because humans have gone to the moon before. This is as far as humans have traveled out into space ourselves so far. A little over 50 years ago, the Apollo astronauts came to the moon, walked around. And when they traveled to the moon, it did take them a couple of days or so to get there, because even though it's our closest neighbor, it's still about 250,000 miles away from us. So everything in space is very spread out. And at the moon, I want to introduce an idea that I'm going to be using throughout the rest of the show here. So as we go on these distances way out into space, they are distances that it's hard for us to even fathom and wrap our heads around. So if I was using terms like kilometers or miles for the rest of the show, it would start to not really make a lot of sense pretty quickly, which you can probably imagine since it's already 250,000 miles to get to the moon. So instead of those measurements, I'm going to be talking about distances the speed of light could go in a certain amount of time. So I'm going to be using light speed as our distance measurement. So for example, if we were traveling at the speed of light, the fastest speed we know of in the whole universe, it would take us about 1.5 seconds to get to the moon from Earth. So we say the moon is about 1.5 light seconds away from us. So roughly the same amount of time that it took us to fly over here in OpenSpace today. But I'm going to zoom us back out away from the moon, and I'm going to bring up some more lines. So we saw the orange line that was the orbit of the ISS around Earth. I'm going to bring up some blue lines that are going to show us the orbits of the moon and also the orbits of the planets in our solar system. And for a moment, I'm going to focus on the center of our solar system, the closest star to us, the sun, and check in with how far we would have to, or how long it would take us to get there if we were traveling at the speed of light. So traveling at the speed of light, it would take us about 8.5 minutes to get from Earth to the sun. So the sun's about 8.5 light minutes from us. And a couple ways to think about that. You could think about it as if the sun just disappeared for some reason, we wouldn't know about it for 8.5 minutes. But thankfully, there's no reason why the sun would just disappear. We don't need to worry about that too much. Or another way I like to think about it is that if you go outside and you look at the sun, first of all, don't do that. Don't look at the sun. It's very bad for your eyes. But if you were to walk outside and look at the sun, that's what the sun looked like 8 minutes ago, not what it looks like right now. So within these few light minutes of distance, we've got the smaller rocky planets in our solar system, Mercury, Venus, Earth, and Mars. And then farther out, there's a pretty sizable gap here in between Mars and Jupiter. But that's not totally empty space. That's where we find most of the smaller rocky objects in our solar system, where we find most of the asteroids in the asteroid belt. And then beyond the asteroid belt, that's where we get to the bigger, gassier planets in our solar system. So we've got Jupiter, Saturn, Uranus, and Neptune. But far out beyond Neptune, I also like to talk a little bit about my favorite dwarf planet in our solar system, Pluto. And to this day, I get lots of questions about Pluto. People wonder, what happened to Pluto? Why don't we call Pluto a planet? Why do you hate Pluto? But I'm here to tell you, I do not hate Pluto. I actually really like Pluto. And there's a simple-ish reason why it was changed from being called a planet to a dwarf planet back in 2006. And one of the main reasons there, I'm going to bring up some trails here. It's going to look kind of bright, just a warning. So these trails are showing us what we call Trans-Neptunian objects. So basically objects that orbit mostly outside the orbit of Neptune. And if you take a look at a lot of these, you can see that a lot of the ones out beyond Neptune out here are orbiting in what looks like maybe a bigger belt, kind of similar to the asteroid belt, but farther out. And that's what we call the Kuiper Belt, which is mostly icy objects with some rocky objects as well out there. Now, we did not know about the Kuiper Belt until the late 90s and early 2000s as we got better telescopes and were able to start to pick out these small, dim objects far out in our solar system. So, as astronomers started to find all these objects, they brought up a question of, well, should we call all of these objects that are around the size of Pluto planets, or should we come up with another category? And what was decided by a group of astronomers back in 2006 is that they would come up with a new category called dwarf planets, which are objects that are, for all intents and purposes, planets, but they have a bunch of stuff in their orbits that they didn't clear out. So, because Pluto has a bunch of stuff in its orbit, that is why we call it a dwarf planet and not a planet. But that doesn't make it any less cool. And we even sent a spacecraft out to Pluto just a few years ago, which is more recent than a couple of the official planets. Uranus and Neptune, we haven't sent spacecraft out to since the 80s. And that's a good point to kind of check in with our human influence again, too, because these are showing us how far any of our spacecraft have gone out into our solar system. So these 5 are the 5 spacecraft that we have intentionally sent them in directions and sent them at a speed so that they will leave our solar system behind entirely. So these are Voyager 1 and 2, Pioneer 10 and 11, and New Horizons, which went out to Pluto back in 2015. But even so, with these spacecraft going incredibly fast and traveling for a while, the Voyager spacecraft left in the 70s, none of them have really gone out yet to a distance that light could travel in about a day. So at this point, we're still looking at light hours of distance. We're not quite out to light days of distance. But we are starting to get questionably to the edge of our solar system at this point. It's a little tricky to try to figure out exactly where our solar system begins and ends, because our solar system has to do with things going around the sun. But we have asteroids and comets going around the sun, but also the sun has a magnetic field and it has a gravitational influence, and there's lots of different factors there. So it can be kind of squishy to try to figure out exactly where the solar system ends. But around here, you may notice the sun started to look a bit different there. So before we were dimming it down so we could actually see the things in our solar system. But now our model has adjusted, so you're seeing the true brightness of the sun. And out here, this is where I would say, without argument, we have definitely left our solar system behind, because you can see that we're starting to fly past other stars that are outside of our solar system. Now, if we were traveling at the speed of light, it would take us quite a while, even to get to the closest star. So it was 1.5 seconds to get to the moon, 8 minutes to get to the sun, a few light hours to get outside of our solar system potentially. Out here, if we wanted to get to another star, that would take us about 4 years if we were traveling at the speed of light. So we're already up to light years of distance, even with the closest stars out there. But we're nowhere close to being done. We have a long ways to go still, so we're going to keep on zooming out. And I'm going to bring up another thing here to show us the locations of which stars have their own planets. So every single one of these blue markers here is showing us the location of a star that we know has exoplanets, what we call planets outside of our solar system. And we've only recently learned about these as well. People thought for a really long time that perhaps other stars would have planets around them, but it wasn't until 1995 that we got confirmation and did observe a planet around another star. And already we're up to over 4,000 exoplanets that have been confirmed, and just as many roughly candidates as well. So for some of these exoplanets, you have to watch them for a while, observe how they move, what their year is like, things like that, to really make sure you're looking at an exoplanet and not maybe a weird sunspot on another star or something like that. So there are thousands and thousands of these, and maybe even billions of them out there in our galaxy. And right around here, this is where I do want to one last time check in on our human influence out in space, because we've seen how far spacecraft have gone. We've seen how far we ourselves, humans, have gone. And now we can see how far anything we've sent out into space has gone. So anything we're going to see from here on out is not because we've sent a spacecraft or a telescope to these places to take pictures or anything like that. Everything we'll see from here on out is because we've looked at these objects in these places with tools like telescopes on Earth or out in space that we have nearby. So all the light is from the light that has traveled to us rather than us going to those places. And the radiosphere, this sphere that I put up right here, this is to show us, though, how far any of our radio signals could have gone out into space. Any radio signals that we send out away from the Earth that are traveling, that are strong enough to escape our planet, they're all traveling at the speed of light. So the earliest of those were sent out in the 1930s or so. So the farthest that any of our radio signals could have gone is within this little sphere here, about 90 light years away from us in all directions. But let's keep on going, and I'm going to turn off our exoplanets here, but I am going to leave on the radiosphere because I do like to keep an eye on it as we zoom away. And in a moment, our view here is going to change. So right now we're seeing the locations of stars that are nearby us, relatively speaking, out there in our galaxy. And we've mapped out those individual stars where they are. But in a second, we're going to see a model that is not based on direct observations or pictures of what we can see from where we are. It's based on what we can see from where we are, but also our best guesses and ideas based on the other things that we see. Because like you saw, we have not sent any spacecraft out here. So this is all just based on the light we can see. So this model of our galaxy, of the Milky Way Galaxy, is what we think our galaxy would look like if you could travel outside of it. And we live in a spiral galaxy, so it's pretty flat. It's got these spiral arms of gas and dust and stars. There's a bunch of stars grouped closer together in the middle of the galaxy. That's why it's so bright in the center. And if you can still see it, do you still see the radiosphere, that little teeny tiny dot kind of near the bottom, about 2/3 of the way out from the center? That's our little human realm, how far any of our communications have gone. And that's because we're now up to thousands of light years of distance. If we wanted to travel from one end of the Milky Way to the other, if we were traveling at the speed of light, it would take us about 100,000 years. But again, not stopping here, we still have quite a ways to go. And as we zoom away from our Milky Way galaxy, we're going to see a lot of other dots start to show up. But at this point, these dots are no longer those individual stars like we saw before. Now, every single dot you're seeing is another galaxy. And every single one of those galaxies has its own billions or sometimes trillions of stars. And if you're wondering about the colors of these galaxies, that's not the actual color of them, though I do think it would be delightful if it looked like cosmic Skittles out there in the universe. But these colors are just a color coding system that we're using for these galaxies. So this is an actual map. We've mapped out where these galaxies are relative to us. And the colors have to do with things like what telescope was used to see that galaxy. So what data set is it part of? Or which group or cluster of galaxies is that particular galaxy part of? Things like that. And even farther out, some of the dots we'll see at the very edge, I think they're all orange if I'm remembering correctly, but at the edge of this in a minute, some of the dots we're seeing will be not galaxies, but quasars, kind of the earliest objects or early objects in our universe, the bright cores of forming galaxies. And as we zoom out, there is kind of a weird shape that you're going to see that seems to form as we look at these galaxies here. It's going to look sort of like an hourglass or a butterfly or a bow tie, something like that. Now, again, unfortunately, I think, because I think it would be delightful, our universe is not shaped like a butterfly. I would like that, though. The shape that we're seeing is because all of this is a map, and it's all from our perspective here on Earth. And because of that, things look a little bit strange. So we've got these large gaps to the left and the right as we look at these galaxies. But it's not because we don't think there are more galaxies over there. We just haven't been able to see them and map them out yet. So in our galaxy, our spiral galaxy, like I said, is very flat and has a lot of gas and dust and stars. When we try to look over in these directions where the gaps are, our galaxy is blocking our view, making it so we can't see over there. So we think there are just as many galaxies over in those directions too, but we just haven't been able to map them out like we can with these other galaxies in the other directions. And this is an interesting spot to point out that as we look at these objects that are incredibly far away, we are probably a few billion light years away at this point, we're also looking back in time in a way. Because all this light has to get to us, right? Has to get into our telescopes. And by the time it travels all this distance and we see it in our telescopes, we're seeing these objects as they looked in the past, not how they look today. So just like I mentioned earlier, that if you were to look at the sun, which again, don't do that, but if you were to look at the sun, That's how the sun looked 8 minutes ago, not how it looks right now. And this is what the universe looked like billions of years ago, not how it looks right now. And because of that, that means there is only so far that we can go. There is an edge to everything we can see in our whole universe. And that edge of our, what it's often called our observable universe, is all over the dome here now, what we call the cosmic microwave background. Now, if you walk outside and it's a clear night and you look up at the sky, you're not going to see this up there in the sky, which, thank goodness, that would scare me if I saw this up in the sky. But if you did walk outside and if you were able to see microwave light, a lower energy form of light that our eyes can't see, but our telescopes can, then you would see this every single place you look in the sky. And this is what I like to think of as the baby picture of the universe. This is what the universe was like a few 100,000 years after the Big Bang, when light was first able to just go out in all directions and expand out away. Everything was in a tiny area and light couldn't really go anywhere before this, basically. So this is the moment where things cooled down and expanded enough, light was able to just spread out in all directions. But since this baby picture of the universe is as far as we can go out into space, that means we can't go any farther. So I'm going to end our journey by bringing us back home. Don't want to leave you stranded out here so far away. And if we were really this far away, and if we were really traveling at the speed of light, this journey home would take us about 13.5 billion years. But thankfully, we're in the planetarium. It should only take about a minute. And one last thought that I like to leave folks with as we fly on back home is that all of this that we've been looking at, all these stars, galaxies, cosmic microwave background, planets, dwarf planets, asteroids, everything that we can see, that's not even everything that we know to be in our universe. There's some really mysterious stuff out there that we know exists and we see evidence of it all over the place, but we're not sure what it is exactly. So things like dark energy, some mysterious force that is causing space to accelerate as it expands. There's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it, especially at the edge of galaxies and places like that. We call them dark energy and dark matter because we're not sure what they are, but we do know that they make up about 96% of our universe. So all this that we can see is a teeny tiny portion of everything that's out there. And that makes folks feel kind of uncomfortable and small sometimes. And I agree, that makes me uncomfortable sometimes as well. But another way I like to think of it is that, well, yes, we are this one very small dot in this gigantic universe. But look at all of this that we have discovered so far, almost entirely by just looking through telescopes. And there's a whole lot more out there to discover and a whole lot more to learn about. And I think that's pretty exciting. But with that thought, I am always a bit relieved when we're approaching our galaxy again and getting back to our familiar little human realm here in the universe of our radiosphere. So now we've got about 90 light years left to go. And we'll head back to that third planet from the sun, which is also the only place in all of this that we have found life at all so far, which is another pretty incredible thing to think about. But with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying around in space with me for a little bit, and I hope you all enjoy the rest of your day. Thank you so much for coming.